Yeah, just a moment, please. Okay, good morning, ladies and gentlemen. Welcome to the visiting lecture today with Arunai Engineering College from India. Welcome to the Honorable Professor Noorul Hassan and to the Honorable Professor Moohambigai. For the topic today is reviewing and analyze deadlock and starvation. Okay, for today's session is being live streamed on the Universitas STEKOM YouTube channel. And now I will note first there will be we will start class presentation by our special guest for today and continue with Q&A session for all students. And next is the time for documentation and last time is closing. Okay, we will start for this class today. Let's begin for Professor Noorul Hassan and Professor Moohambigai. The time is yours. Thank you.
Good afternoon to one and all present over here. And here I am Moohambigai, Professor of AI&DS and Cyber Security. Can you hear my voice?
Yes.
Okay, sure, ma'am. Okay, so I'll be the speaker of today. Okay, I belong to an Arunai Engineering College, Thiruvannamalai, and Professor of AI&DS and Cyber Security. And today I'm going to handle the session for you regarding the deadlock and starvation problem in operating system. Shall I start my session, ma'am?
Yes, Miss.
Does my screen is visible for you, everyone?
Yes, it's invisible.
Oh, sure. Okay. Today we are going to deal about deadlock. Okay, so which is the most problem in operating system. So these are the topics that we are going to discover in deadlocks. So the first one we are going to deal about system model, second deadlock characterization and methods for handling deadlocks, deadlock prevention and avoidance, detection method and recovery from deadlock and starvation. Okay, so and the problem for starvation is aging, that we'll see it in later slides. So the main objective of this thing is that, so first we need to have a description of a deadlocks. So and then what are the different methods for preventing or avoiding the deadlocks in a computer system? Because these are the two topics that we are going to cover major in this session. The first one is that here I have given a real-time scenario of a deadlock. So here there are two persons. So one is Emmy and second one is John, right? So if Emmy wants a laptop, so the laptop it's at present it is held by some other person John. Similarly, likewise, the John wants the remote, but remote is actually held by Emmy. So here I can consider these two persons as a process. So in case of an operating system, okay, the process P1 may be Emmy and the process P2 may be John, and the resources may be the laptop and then the remote. The laptop may be here I consider the laptop may be R1 and then the remote may be R2. So now consider this scenario. Emmy wants the laptop, but the laptop is currently it is available with John. Likewise, John is having the remote. The remote is currently available with Emmy. So if both of them needs a resource simultaneously, it is not possible, right? A resource requested by an Emmy is currently held by John. Likewise, a resource requested by John is currently held by Ami. So this we call it as a deadlock situation. So when you consider this, so here we'll be having a circular or a cycle, right? So consider the arrow mark from Ami to laptop and from laptop to John and from John to remote and then from remote to Ami. So this results in a circular fashion. If this fashion exists in a OS scenario, that causes a deadlock. Okay, so this is a simple example I have given you for your understanding purpose. And now, when you consider your system, so normally we'll be having many resources. So we can classify the resources into hardware resources as well as the software resources. So here the resources may be numbered from R1 up to Rn. So here the software resources may be CPU cycles, memory space, etc. And the hardware devices may be IO devices. So that may be your printer and then keyboard, monitor, etc. like this. So whatever it may be, either a hardware resources or a software resources, all can be comes under the category of a resource type. We can number each and every resources from R1 up to Rm, right? So and then the next thing is that I can say that if I can have more than one printer at instance. So here each resource type Ri has W instances. So we may have more than one printer, right? So we can say that the printer may be of resource R1, which is equivalent to 3, indicates that we are having 3 printers. So the instances represents the number of printers or number of resources that we have. Okay. So suppose if the process want to utilize a resource, if the process. So the first thing is that you need to know a distinction between a program and then process. So a program is nothing but a set of instructions. So set of instructions that have been written to solve a given problem. So that we call it as a program. Okay. So when you consider a process is nothing but a program in execution. So we can say a program is a passive entity and a process is an active entity. So why we are saying it as an active entity is that whenever we assign a processor to a process, we that will automatically become as an active one. So that we call this as an active entity, right? So each and every process within the system can make use of a resource. So if it want to make use of a resource, the resource may be requested in particular order. So the first order is that request the resource. If the resource is available, use that particular resource, and finally after making utilization of those resource, release that particular resource. So this is the order each and every process may request a resource. The first one is request, and then use the resource, and then finally after making it use of the resource, release the resource. That resource may be utilized by some other process. Okay. And then so these are the more four conditions that are necessary for occurrence of a deadlock. So the first one is that mutual exclusion, and then the next one is that non-exclusion, and then the next one is that non-exclusion, and then the next one is that and then the next thing is that hold and wait. So previously I have given you a simple diagram and then John, right?
Good morning,
So
Miss.
me holding a particular resource laptop, and she's holding the remote and she's asking for the resource laptop, right? So likewise, we may
And
be having two different
I'm
resources.
sorry, Miss, for disturbing. Oh, yeah.
Ma'am, I
Could
can't
you
hear you.
could you share your presentation again?
Shall I want to repeat it again, ma'am?
Could you share your presentation again? Or maybe you can check your room chat.
Sorry, ma'am, I can't hear you. Is it visible now? Does my screen is visible for you, ma'am?
Could you share your presentation again?
Could you share the screen again?
No, aku.
One second, ma'am. I'm sharing it again.
Yes.
Now now is it visible, ma'am?
Yes.
Okay. Where shall I start? From the beginning?
Yeah.
Shall I start from this?
Yes, Miss.
Okay, sure. Let me consider these two persons, right? So these two persons is the process. So ME may be a process 1 and then John may be a process 2. Okay. ME is in requirement of laptop and likewise John is in requirement of remote. But the laptop is currently held by John and likewise the remote is currently held by ME. So both are in need of the resource which is held by the other persons. If any one of the persons leave the resource only, they can make utilization of both the resource. So when you consider this deadlock situation, it will result in a circular fashion, right? So we are having an arrow mark from ME to laptop and likewise from laptop to John and from John to remote and from remote to ME. Okay, if this cycle exists, we can say that definitely a deadlock will occur. Likewise, when you take an operating system, if there are two resources and two persons, just like this, when you draw a graph, if it results in a cycle fashion, automatically we can say that a deadlock will happen. So if a deadlock happen, we cannot assign the resources to that particular process. Okay. And then here we can say the system model. The system in the particular system, we can say we can consist of n number of resources. So the resources may be hardware resource or it may be a software resource. The hardware resources may be your monitor, your printer, and then mouse, etc. And suppose when you take a software resource, it is nothing but your CPU cycles and then memory space, etc. So we can group all together as a resource. So when you take a particular resource, for example, if you take a particular resource as printer, we may have more than one printer. So that more than one count can be denoted by instances, right? Each resource type Ri has Wi instances. Suppose let me consider that Ri is nothing but a printer and Wi equivalent to 3, which indicates that I'm having 3 printers. Okay, so each and every process can make use of a resource. So if it want to make use of a resource, it should be in a particular order. So the first one is that a process should request a resource, and after making a request, if the resource is available, it can make use of that resource. So once the resource has been utilized by that process, if it is no longer needed, it can
Dan jangan
release
lupa
the
Bapak Ibu
particular resource.
aktifasi komunitas belajarnya. Yang
This may
paling
be
minimal itu adalah komunitas belajar yang ada di dalam
now
sekolah
I
Bapak
think
Ibu. Misalkan Bapak
someone
Ibu
writes
membuat komunitas belajar berbagi SD ini, SMP ini atau komunitas belajar
I'm
antar
hearing someone.
sekolah atau antar kabupaten. Kalau antar sekolah mungkin ada KKG
And
ya yang itu pasti mereka yang Bapak Ibu mulai menyusun kurikulum satuan pendidikan dan rencana pembelajaran secara bertahap. Bapak Ibu kita contoh yang sudah ada di platform Merdeka Belajar Bapak Ibu sesuaikan dengan sekolah Bapak Ibu. Selanjutnya di fase ada fase implementasi. Nah di sini Bapak Ibu telah secara fase perencanaan ini ada fase implementasi. Di sini Bapak Ibu mulai menerapkan kurikulum Merdeka untuk meningkatkan karakter dan profil. Nah setelah Bapak Ibu melakukan implementasinya.
I'm hearing some more noise. Shall I proceed now? Novita ma'am, shall I proceed now? Am I audible? Okay, I'll start the session now. And then suppose if a process wants to make use of a resource, that resource requisition should be in a particular order. The first one is that it should request the resource. If the resource is available at that moment, that resource may be utilized by that process. And after making use of that particular resource, it can release the resource because that resource may be in need of by some other process. Okay, so this is the order that should be followed by each and every process while making use of that resource: request, use, and then release. And here these are the four characteristics, or we can say that these are the four conditions. If these four conditions exist, definitely we can say that a deadlock will occur. So this we altogether we call it as a deadlock characterization. So the first one is that mutual exclusion. So only one process at a time can use a resource. If there are more than one process, so if there is a single resource, only one process can use that resource at a time. Okay, if it is needed by some other resource, and if it make a request at the same time, automatically a deadlock will occur. So there should be a mutual exclusion between two different processes which is competing for the resource. And then the next thing is that hold and then wait. A process holding at least one resource is waiting to acquire additional resources held by other processes. That might have been shown in the previous slide. So here AMI is nothing but a process 1, and John is nothing but a process 2, right? AMI is in requirement of the resource laptop and John is in requirement of the resource remote. But either of these two resources are held by the other persons. So we can say AMI is holding one resource and is requesting one more resource, right? Likewise, John is holding one resource and requesting another resource. So this condition is nothing but an hold and then wait. A process is holding one resource and waiting for the other resource to start its execution. And then the next one is that no preemption. Whenever a resource, so when we consider a no preemption, whenever a resource is assigned to a process, the process can only voluntarily release that particular resource if it is no longer needed by it. Okay, so no preemption, it can release the resource only voluntarily when it is not needed by it. So this we call it as a no preemption. And then the next thing is that circular wait. So since we know that there may be n number of process, that process can be numbered from P0 up to Pn. Okay, so when you consider this, so I have given you a simple diagram is that, so totally here there are three different processes, P1, P2 and P3, and three different resources, R1, R2 and then R3. So according to this scenario, you can examine that the process P1, from P1 I am having an arrow mark to R2, from R2 to P2 and P2 to R3 and R3 to P3 and P3 to R1. So this we call it as a circular wait, which indicates that P1 is requesting the resource R2, but R2 is assigned to P2. P2 is requesting the resource R3, wherever R3 is assigned to P3, and P3 is requesting the resource R1, and R1 is assigned to P1. So this automatically creates a cycle. Okay, so it is holding one resource and requesting another resource. That resource is held by another process. So likewise, if this condition exists, then automatically a deadlock will occur. So these are the four different conditions that is necessary for the occurrence of a deadlock. And then the next thing is that resource allocation graph. So here we can say that what do you mean by a node and what do you mean by an edges. A node is nothing but a vertices, right? Edges is nothing but the line connecting the nodes, we call it as an edges. So we can say that B is partitioned into, that is the vertices is partitioned into two types. So that is process and then resource. The process, as I said, that there may be n number of process, so we can number the process from P1 up to P1, so which is the set consisting of all the process within a system. And likewise, we may be having n number of resources, R1 up to Rn. So this is nothing but the set consisting of all the resource types in the system. And here we should deal with two different types of an edges, that is request edge, and then another one is that assignment edge. So when we consider request edge, so there is a directed edge from Pi to Rj. So listen here. So when you consider this diagram, so this edge we call it as an request edge. So P2 is requesting the resource R3. So this we call it as a directed arrow which is proceeding from P2 to R3. So this we call it as a request edge. Okay. So and then the assignment edge. The assignment edge is just the reverse of requested edge, the directed edge from the resource to a particular process. So here from R3, there is an arrow mark or directed edge to P3. So this we call it as an assignment edge. The resource R3 is assigned to P3. So this we call it as an assignment edge, and here this we call it as an request edge. The process P2 is requesting the resource R3. So I hope so you should know about, you're clear about the requested edge and then assignment edge. And then this is the simple diagram which shows about how to deal with a deadlock. So each and every process is denoted by a dashed circle, okay, which is filled with some colors, or we can say it is denoted by a circle. A process is generally denoted by a circle, and here comes the resource type. So resource type with 4 instances. For example, so let me take a printer. So a printer, the number of instances of printer is equal to 4. So I can say that according to this diagram, it is denoted by a square shape. Okay. So this indicates that there are 4 printers. And now, so PA request instance of RJ. So instance of RJ is that the count, that is the number of resources of that particular type. So here when you take this as a 4 printer, now PA request an instance of RJ indicates that it is requesting one of the resource of RJ. Okay, I'm requesting one printer of that particular resource. And then the next thing is that PA is holding an instance of RJ. So here, listen here, directed edge follows from the resource to a process. Okay, so here we call this as an request edge, and which in turn here this is nothing but an assignment edge. And then how can we draw the resource allocation graph? So as I said in previous diagram, each and every process should be denoted by a circle, okay, and each and every resource is denoted by a rectangular, or it may be a square box. Okay, so this dot indicates that the number of instance of that particular resource. This single dots indicate that there is a resource R1 which is of only 1, and here there is a resource R3 which is of only 1, and here when you consider this one, there is a resource R2 whose count is equal to 2. Okay, so accordingly we can draw. So totally we are having 3 different number of process which is denoted by P1, P2 and then P3, and then resource R1, R3 and then R2, where we are having a single instance R1 and then single instance of R3 and 2 instance of R2. Okay, so if a process P1 requests an R1, it indicates that we should draw a directed edge from P1 to R1. And if suppose if I'm saying that R1 is assigned to P2 அப்படினா, will be getting an directed arrow mark from R1 to P2. Okay, likewise we can draw a diagram. So this we call it as an simple example for resource allocation graph. According to the given scenario, we can draw the diagram. So when you take a scenario, they will say that how many number of processes will be available, how many number of resources will be available, and for each and every particular resources, how many number of instances it should be there. Accordingly, we can draw the diagram. And here there is one more resource, that is R4, which is never needed by any one of this process. So it is simply we have drawn that, that is R4 is a resource which is here we are going to have 3 instances of R4, which is not requested by any process or which is not assigned to any other process. So that's why it is simply it is given as it is. And when you consider here, this is a resource allocation graph with a deadlock process, right? So when you consider this diagram, P1 is requesting the resource R1, R1 is assigned to P2, P2 is assigned to, P2 is requesting the resource R3, R3 is assigned to a process P3, and P3 is requesting the resource R2. See, listen here. So when you consider this diagram, R2, so totally in R2 we are having 2 different instances, right? So here R2 is assigned to one process P1 and one more R2 is assigned to another process P2. Okay, if in this scenario, if a request from P3 arises, automatically
Yeah, good morning, Miss. Maybe you can turn on your microphone because we cannot hear you. Thank you.
Can you hear my voice?
Yes,
Okay, shall I proceed, ma'am?
yeah, you can share your PPT again, please.
I can't clearly hear your voice. Can you be louder, little bit louder?
Yes, you can. We can hear you, and
Ah,
you
okay.
can share your PPT again. Thank you.
Okay, ma'am. I'll proceed now. Okay, so here come I said that. So even though a cycle exists, so even though here it forms a cycle, that is R2 to P1, P1 to R1, and R1 to P3, and P3 to R2, and deadlock will never occurs because here I'm having one more instance that may be requested by a process P3. And then, so these are the simple basic facts about the deadlock. If a graph contains no cycle, we can definitely say that there is no deadlock. Okay, so when you consider this diagram, so if the cycle exists or if the cycle doesn't exist, we can say there is no deadlock. Okay, if a graph contains cycles, if there is only one instance with resource type, then a deadlock will definitely occur. Or else, if the resources of maybe of several instances, there is a possibility of a deadlock, but the existence of a cycle says that a deadlock sometimes may occur or may not occur. It depends upon the number of instances of the resources. So that might have been shared here. Even though a cycle exists, a deadlock may never occur because there may be one more instances of that particular resources. So that is given here. So if several instances per resource type, there is a possibility of a deadlock, but we are not sure that it will definitely happen. And then suppose if a deadlock occurs, so what are the ways we can avoid the deadlock? Okay, so first thing is that take a mutual exclusion. So it must hold for only, suppose if we said that it must hold for only non-shareable resources, you can automatically prevent the deadlock. And when you consider the hold and wait process, so suppose if a process starts its execution, if the process is going to start its execution, before start its execution, it should have all the resources requested by it. For example, if it is in requirement of R1, R2, and R3, all the resources must be assigned to that particular process. Only then it can start its execution. Okay, so once it finishes its execution, it can releases that particular resources. If we do just like this, we can automatically avoid the deadlock. Okay, okay. So and then the next thing is that no preemption. So what I said previously is the no preemption. If I am using the resource, I should voluntarily release that particular resource if I am not in needed of it. Okay. So likewise, so suppose if I am holding some resources, if I am requesting another resources, that resources may not be immediately allocated for me, then I should release the particular resources held by me. Okay, so if I am requesting the resource, I repeat it, if I am requesting a new resource, if that new resource is not available at that moment, I should release the resource which is already held by me. Okay, automatically the deadlock will be clear. And then, so when you go for a circular wait, we can give a total ordering of all the resource type. Ordering is nothing but a numbering of the resources, that is P1, P2, P3, and then R1, R2, R3. So this condition we'll see it in the next upcoming slides. So that is Banker's algorithm. So that will be quite interesting, and it is also very important concept while you're dealing with a deadlock. So when you make a false of these four conditions, that is no preemption, circular wait, and then hold and wait, and then mutual exclusion, automatically the deadlock will be prevented. And then, so the deadlock avoidance. So this deadlock avoidance is a very important and interested topic. So here, before assigning resources, or before assigning before just determining the number of process, we should have a prior requirement. So the prior requirement is that we should initially we should specify that how many number of resources available and how many number of process available in that particular system model. So here I've said that the maximum number of resources of each type should be known to the system in a prior manner. So if we are going to deal like this in this manner, we can automatically eliminate the deadlock. I'll show you with the help of a simple example. Okay. So this algorithm, we call it as one of the most important algorithm is that Banker's algorithm, which deals with the deadlock avoidance. So in deadlock avoidance, we are just going to look upon to the safe state. If I am going to assign the resource to each and every process in a particular order, whether a cycle exists or not, we should first check that if I am assigning hear your voice. Am I audible, ma'am?
Yes, Miss.
Yeah, okay. Okay.
Thank you.
So, before allocating a resource to each and every process, we should check that whether there exists a safe sequence. So, when a process requests an available resource, the system must decide if immediate allocation leaves the system in a safe state. Suppose if I am having n number of process, that is P1, P2 up to Pn. If a process Pi requests a resource, if a process Pi requests a resource, so that is held by some other process Pj, so that process number should be less than Pi. For example, if a process P2 is requesting a resource that is held by process P1, so we can compare the identity of P2 and then P1, right? P2 is requesting the resource which is held by the process P1. Compare the identity. So now the requesting resource value is greater than there is a process which is holding the resource, that is P2 is greater than P1. In that case, we can automatically assign the resource. Okay, so this is what I've said, that J should be less than I value. If PI is requesting the resource that is held by the process PJ, then the PJ value should be less than I. So what here I'm insisting to say that if the resource PI, sorry, if the process PI resource needed or not immediately available, then the process PI have to wait until the PJ have finished. If I am requesting the resource, if that resource is particularly held by some other process, I should wait, right? So that is the real case scenario. If anyone is having the resource, if anyone is having the pen, if I need the resource pen, if it is not currently available, I should wait, right? So that is explained here. If the process PI requires the resources that is not immediately available, then the process PI should wait until the PJ have to finish. Okay, so once the PJ is finished, when the process, another process is finished, the PI can obtain the needed resources, execute it, and return the needed resources and terminate. So that I have seen in the said in the previous slide, that is request, use, and that release the particular resource. This is the order each and every process should claim. So this is some of the basic facts. If a system is in a safe state, we can say that there is no deadlock. We should find the sequence that in which particular order we can assign the resources to each and every process. For example, if I am having three different processes, P1, P2, and P3. If I am assigning the resource to process P1 and then followed by P2 and then followed by P3, if there exists a safe sequence, we can say definitely a deadlock will never occur. Or we can try some other possibilities, P3 followed by P2, P2 followed by P1. Whatever it may be the case, this safe sequence will be determined with the help of an banker's algorithm. Okay, so if a system is in a safe state, we can say that there is no deadlock. If the system is an unsafe state, there is a possibility for deadlock. So we can avoid the avoidance can be made, that is we should ensure the system that will never enter into an unsafe state. So this is a simple diagram. So which shows that what I mean by a safe state and then unsafe state. A safe state says that there is no possibility of an deadlock, whereas an unsafe state may lead to an deadlock. But just remember that if there exists a cycle, there is a possibility for a deadlock, or a deadlock will never occur if there is multiple instances of that particular resource. Okay, so here we can classify the avoidance algorithm according to the number of resources. Suppose if there is only one single resource of only one instance, we can directly use the resource allocation graph. What I've said in previous slide, and each and every process is indicated by a circle and resource is indicated by an circle that is rectangular, or it is nothing but a square box, right? So suppose if there are more instances of more resources, we can directly go for the next algorithm, that is banker's algorithm. This is very important algorithm. Okay, so here one more thing is that claimage. So a claimage is similar to one, so I can explain this with the help of this diagram. So suppose here there are two processes, that is P1 and then P2, and then R1 and then R2. Okay, so what I said previously, R1, if there is a directed edge from R1 to P1, it is nothing but an assignment edge, right? R1 to P1, this is an assignment edge. If there is a directed edge from P2, that is process to resource, it is nothing but an that is request edge, right? So request edge, and this is nothing but an assignment edge. Here there is one more edge that is denoted by a dashed line, that we call it as a claim edge. A claim edge is also and a dotted arrow mark from the process to the resource. See, listen here, which indicates that the process P1 may require the resource R2 in future. Okay, so if it requires the resource in future, we can denote it with the help of a dash lines or dotted lines, that we call it as an claim edge. So this is nothing but an request edge, this is nothing but an assignment edge, and this is an claim edge. The claim edge is that in future it can be directly converted into an requested edge. So according to this diagram, I can say that, so both P1 and then both, that is P1, the process P1 is in need of the resource R2 in near future. So it can be automatically converted at any time into one request stage whenever the process made a request for the resource R2. Okay, so here we can directly deal with the Banker's algorithm. In Banker's algorithm, we'll be having n number of process and n number of resources. So n number of instances of an resources. So we should say that what are the maximum number of processes that we are going to have in a particular model, and what are the maximum number of resources, and the number of then the count of that particular resources. So when a process requests a resource, it must have to wait. So when it gets all the resources and make use of the resources, it should return the resources after a finite amount of a time. So this should be the first scenario of Banker's algorithm. And then according to this algorithm, we'll be making use of four different criteria or four different variables, that is available, max, and then allocation, and then need. So available is that the total number of resources that is available at a particular instance, that we call it as an available. Total number of resources available and the number of instances of the resources altogether, we call it as an available resources. And then max is nothing but at a particular time a process may request at most k instances of a resource type. So that is, I can at the particular moment I can request only 3 printers. So that is the maximum number of resources that may be required by the process at a particular time. So this is the overall number of resources available at a particular system model. This is the maximum number of resources that might be requested by the process P1. And allocated is nothing but the number of resources already allocated to that particular process. So that we call it as an allocation. And need is that at the current moment I am in need of a printer one, only one printer. I am in need of the printer, sorry, tape drive, that is one, etc. So automatically we can say that we can calculate that need equivalent to maximum minus allocation. So this is the formula that we are going to use in a Banker's algorithm, need equivalent to max minus allocation. And this is the algorithm, that is steps. We can start from the available resources. So the available resources is assigned to work, and then finish of I equivalent to false. So this I'll explain this with the help of a simple problem. Okay, so these are few steps, and when you go for the third step, work equivalent to work plus allocation, and finish of I equivalent to true, and finally if finish of I equivalent to true, then the system is in a safe state. So let us see with a simple example, it might be more clear for you. Okay, so here I've taken 5 processes. The process numbering starts from P0 to P4. So totally P0, P1, P2, P3, P4. So totally there are 5 processes, and there are 3 resources types. So the resource A, resource B, and then resource C. In resource I am having totally 10 instances. That is, for example, if I am saying that if this is a resource A is nothing but a printer, it indicates that I am having 10 printers. Okay, if I'm having B as a mouse, I'm having 5 mouse, and then C, whatever it may be, right? So at a given time, for example, I'm taking at a given time T0, these are the allocation to a process. That is, according to this, there are the resource A, B, and C. For a process P0, 0 resources assigned. That is, 0 resource of type A is assigned. Okay, I'm not assigning any resource of A to the process P0. And here, one resource of type B is assigned to P0. So this is the allocation which says about the numbering of each and every resource which is assigned to the process P0, and here this is for P1. So according to this diagram, according to this values, I can say that I have assigned 2 resources of type A to P1. So, and no resources of type B and C is never assigned to P1. So this is the already allocated resources to the process P0 up to P4. Okay, So this is the maximum number of resources that I can request. So maximum number of resources of type A can be requested by the process P naught is nothing but 7, and for the resource B is nothing but 5, and the resource equivalent to C. Okay, and what are the remaining available? The remaining available resources is nothing but the resource A of type is equivalent to 3, and the resource B of type equivalent to B, and the resource C of type equivalent to C. So these are the now currently available resources. From this available resources, any one of the process can request those available resources and add according to their requirement. So we'll see this. Okay. The first thing is that we need to calculate the need matrix. So need is nothing but a max minus allocation. Okay. So when I consider P naught, so when you take max value for P naught, what is the max value for P naught? That is 7, 5, 3. Max minus allocation. So 7 minus 0. Okay, 7 minus 0 is 7. And then 5 minus 1 is nothing but 4. And then 3 minus 0, it is nothing but 3. Okay, so that I have shown in the next diagram. See, listen here. 7, 4, 3. That is the max value should be subtracted, the allocation value should be subtracted from the max value. So accordingly, I have calculated all those need value for the process P naught up to P4. This is the final save sequence that I have found out. But before going on to that, I'll show you how we'll do this. Okay, so let us start. So totally we have said that totally we are having 5 different processes, that is P naught up to P4. Okay, so starting from that, we should first calculate the need value is less than or equivalent to work value. Okay, so if it becomes true, we can calculate work equivalent to work plus allocation. If it is going to be false, we cannot calculate a new work value, that is work equivalent to work plus allocation. So now let us consider the first process P naught. What is the need value for P naught? We should first check that need value is less than or equivalent to work. Work is nothing but an available. Okay, what is the need value for P naught? P naught is nothing but 7, 4, 3. Okay, so and here the available value, that is nothing but 332. So now I am checking that whether 743 is less than or equivalent to work. So the work is nothing but it is equivalent to the available resources. So here you should check or you should compare each and every individual value, whether 7 is less than 3 and 4 is less than 3 and 3 is less than 2. Automatically we can conclude that this is wrong because 7 is greater than 3, right? If any one of the particular value becomes false, we can automatically reject this and we can move on to the next process P1. Okay, so now take the need value for P1. So what is the need value for P1? So according to this, so the need value of P1 is 122, right? So I am checking that 122, which is less than or equivalent to, that is work value, that is available 332. Here just make a comparison. 1 is less than 3, okay, it becomes true. 2 is less than 3, again it becomes true. 2 is less than or equivalent to 2, again it becomes true. When all the values becomes true, we can calculate the new value, that is work equivalent to work plus allocation. So what is the previous work value? 332. Okay, so plus the allocated value. So allocated value, we can go for the first one. For P2, what is the allocated value? Sorry, for P1, what is the allocated value? That is 302. Sorry. Okay. So the allocated value for this is 200. So automatically we'll calculate work plus allocation. So just add these two values, that is 3 plus 2, 3 plus 0, and then 2 plus 0. So we'll be getting a new work value, that is new available value. So when you go for the next process P2, again you'll check the P2 need value. So 600 is less than or equivalent to new work value, that is 532. Automatically this will become false. So again, if it becomes false, we'll go for the next process P1. So before moving on to this, we'll check what are all the values, what for which process the values will become true. So first thing is that for P1 it is true. So we can add this in a safe sequence, that is P1. Okay, because P2, P0 becomes false, we should not add this in a safe sequence. So first P1 gets the true value, add this in safe sequence. Okay, again accordingly, likewise we can calculate for all the process, and then so first P1 followed by P3 and then followed by P4. So finally, we'll be going on to a next circle value P naught, because we have completed starting from P naught and then P4. We are, after completing that, we should again give one more cycle that, so for which process it becomes false. Again for P naught it becomes false. So we are giving one more chance to P naught. So now the P naught need value is less than or equal to new work value. Again the condition becomes true. So we are just calculating work equivalent to work plus allocation. We'll be getting a new value 755. Okay. So I can add this in a safe sequence. So first P1 it becomes true. So P1, and then P3 it becomes true. So P3, and then P4 it becomes true. Add this in safe sequence, and then P0, add this in safe sequence. Okay. So finally I can go for the P2, which has already becomes false. So finally this P2 will add and be in a safe sequence. So this safe sequence states that if I am allocating the resources in this order, that is, first I can allocate the resources, available resources, to the process P1. So it will finish its execution and release all the resources currently held by it to the next resource. So the next turn it takes for the process P3, followed by P4, P0, and then P2. If I follow this sequence, I can definitely say that a deadlock will never occur. You can try for some other possibilities, but automatically it will lead to a deadlock. So before checking that if a deadlock occurs or not, we should check for the safe sequences. If we assign in this particular sequence or particular order, we can say that a deadlock will never occur. Okay. And then the next thing is that deadlock detection. This is somewhat light variation of a deadlock avoidance system. So under deadlock detection, we should first allow the system to enter into a deadlock state, and we can make use of the detection algorithm to check where the particular deadlock will occurs, and if a deadlock occurs, we can recover from that particular stream. Okay. So similar, we can go for a wait for graph. So previously I've said that a process is denoted by the circle P5, and then R1, R2, R3, that is resources indicated by normal spy shape, etc. like this, right? So consider this scenario. This we call it as a resource allocation graph. Listen here. So here a process P1 is requesting the resource R1. R1 is assigned to P2. So I can directly cut these two edges. I can directly cut these two edges, and I can give a directed edge from P1 and P1 to P2. Okay. I hope so it's clear. Listen. P1 is requesting the resource R1, but R1 is assigned to P2. Okay. So which indicates that a process is requesting the resource R1, which is held by the another process P2. So I can directly make a connection between P1 and then P2 by means of cutting these two resources. So I can draw P1 to P2. Okay. So similarly, when you take this scenario, P2 is requesting the resource R4 and R4 is assigned to P3. I can directly cut these two edges and draw a directed graph from P2 is assigned, that is a directed edge from P2 to P3. Okay. So like this, I can draw a corresponding wait for graph. So that is resource allocation graph. So this will be clear for you, I think so. Okay. So here, when you consider this one from P2, P2 is requesting R3, but R3 is assigned to P5. So I can cut the, I can indirectly, I am saying that I am depending upon the process P5 because the P5 is holding the resource R3. So I can directly draw an edge from P2 to P5. So this is the corresponding wait for graph. That is, they are simply simplifying the graph in such a way that it will be very clear for that user, because this will be more quite complex, right? So I can say that whether I am depending upon any other process for a request to be resource to be requested or resource to be released. So this says that P1 is requesting the resource that is held by the process P2. P2 is requesting the resource that is actually held by the process P3, which in turn P3 is requesting the resource that is held by the process P4. Likewise, P4 is requesting the resource that is actually held by the process P1. So I can cut it off, and I can simplify my diagram and give the corresponding wait for graph. So this we call it as a resource allocation graph. This we call it as a wait for graph. And likewise, we have seen in bankers algorithm, right? So likewise, here we can say here is also we are going to have a similar algorithm, that is deadlock detection algorithm. So here I have not included any problem regarding this, because when you go for your examination purpose, you'll be automatically having an deadlock avoidance problem. This is like was similar to an banker's algorithm problem. Okay. See here also we are having an allocation request available, and here instead of need matrix, here we need to find out an request matrix. Okay. So suppose if I have determined a deadlock, how can I recover from the deadlock? Okay. So there are various possible ways. The first thing is that about all the deadlock processes. So according to the safe sequences, or we can say that if a cycle exists, or if there is a condition that is hold and wait, we can say that automatically a deadlock will occur. So in that particular condition, we can identify what are all the processes involved in that deadlock. We can directly identify those processes and abort all those processes. Abort is that just kill that process. Okay, kill all the deadlock processes. That is one case. And another one case is that abort one process at a time until the deadlock cycle is eliminated. Here I can abort all the processes. For example, so if there are 4 processes involved in the occurrence of a deadlock, P1 up to P4. In first case, we can abort all the process, that is P1, P2, P3, P4. We can abort all the process. But in the second case, so we just abort one process and check that if a deadlock cycle is eliminated. If I eliminate a process P1, check that whether a cycle exists or not. Okay. If a cycle doesn't exist, we can leave it as a safe sequence. Even though if it the same deadlock exists, we can go for the aborting the next process, and then again check that whether a deadlock cycle is available or not. Likewise, we can eliminate or we can check each and every stages until a deadlock cycle is eliminated. So that's the difference between the first condition and then second condition. Here about all the deadlock process, but here about one process at a time until the deadlock cycle is eliminated. Okay. And next comes the next question comes that to which process I should abort, because there may be a number of process, right? So which process should we choose? We need to abort. So here there are various cases. So based upon the priority of a process, this is one method. Suppose when you take an academic line, right? So when you take an academic line, you'll give a priority to your higher official. So when compared to a student, right? So if you consider a higher official as a process P1 and if you as a process P2, so you are giving the priority to the higher officials P1, right? So if a particular resource is available, automatically it is visible that you can provide the resources to the higher officials instead of you, right? So according to the priority, I can select the process to be aborted. So the lower priority process is automatically aborted. So that deals with the priority of a process. First one, and then second one, how long the process is concluded and how much longer to completion. Suppose if a particular process starts its execution, right? If it runs for 100 milliseconds and if it requires only 15 milliseconds to complete its execution, this is the scenario of one process. Okay, if the process P1 started its execution of about 100 milliseconds and it requires 50 milliseconds to complete its execution. This is one scenario. And suppose when you take a process P2, okay, it has started its execution and runs for only about 25 milliseconds. In this scenario, we can choose the process P2 because the process P2 has completed the execution of about only 25 milliseconds, right? So if there is a critical situation that whether I need to choose the process P1 or process P2, in such a case I can prefer only P2 because it has run for a little bit amount of time. Okay, so how long the process it has computed and how much longer it has to complete. So based upon that, and then the resources that process has used. So what are the resources that it has already used and what are the resources it requires to complete its execution, and how many processes will need to be where we will directly randomly select a process. So while we are aborting a resources, we cannot directly randomly select a process and abort the resources. Okay. And then so here how can we recover from a deadlock is that selecting a victim. So that is minimize cost. So that I've said a previous example that if you are giving a priority to a particular process, we'll choose the low priority process to be aborted. So that low priority process we call it as a selecting a victim. That should minimize the cost. Okay. And then rollback is nothing but so return to some safe state. Okay, so from that safe state we can restart the process. So in deadlock avoidance problem, in banker's algorithm problem, we have solved it, right? So for some process, automatically the values goes wrong. So that is need is less than or equivalent available goes wrong. Okay. So once a particular sequence have been executed, we'll again give a chance to that process, right? Roll back to that particular save state, and again we have started from that process. So this is one thing. And now the third one is that starvation. So this starvation is nothing but starvation. The general meaning is that you're longing for something for a indefinite period, right? So suppose, assume that if the same process have been picked up as a victim for a n number of times, right? So that particular process will never get a resource for its execution. We can say this as a starvation. Okay, it will be, that is, it can be selected as a victim for n number of times for an indefinite period of a time. We can say this as a starvation. Okay, so that is I have given it out. So the starvation in operating system occurs when a process waits for an indefinite time to get the resource it requires. It will never get the resource after a long period of a time. Okay, so this status we call this as a starvation. So this is one of the scheduler issue. The scheduler is here nothing but a CPU scheduler issue, right? So here the another name for starvation is also called as a light lock. So here I will show you a simple diagram. So totally I've taken 5 different processes, right? So initially I'll be having a process likewise each and every process. So here I have given only with the priority, priority 1 process, priority 2, priority 3, and then priority 5. Assume that currently it is executing. Okay, if a new process with a low priority keeps on coming, then a process with the priority 5 will be starved. If I assume that a new process will arrive with a priority number 4, here you should consider that a lower number indicates the higher priority, right? Your academic head will have a priority 1. The number 1 is a least number, but the number 1 is going to have a high priority. Am I clear to you? Okay, this is high priority. So the priority 4 process when compared to the priority 5, so just compare the number. This is required by it. Okay, so always wait. If new process with a low priority keeps on coming, then a process with a high priority starve. This is the lowest number which is having a high priority. While these processes are executing, gains the access. So finally, the priority 5 process will never regain the resources required by it. Okay, so always wait. If new process with a low priority keeps, so this we call it as a starvation process. By increasing the priority of a process, suppose if you we can automatically increase the priority, right? The process is assigned the priority value 5. So we are enquiring that if a process will never get a resource, we can increase the priority by reducing the number. Okay, so as I've said that least number indicates the higher priority. So this is one method, or else we can choose the process at random, allocate the process or the resources to that particular process. So this is way we can either increase the priority of a process, or we can assign the resources to the process by choosing it randomly. See, these are the two ways to control the starvation. And one more thing is that aging technique. So aging technique for process, what I've said previously, after watching for a predefined amount of time, if the process never gets the resource, automatically we can increase the priority. That we call it as an aging. But what are the limitations of aging? That is increasing priority of a waiting process, because we need to automatically we need to change the priority of each and every process after watching the starvation situation of the particular process. Suppose when I watch the process P1 after 2 hours, since it is in the same case, if it is not getting the resource, we need to increase the priority. Likewise, for all the process, we need to watch and increase the process, increase the priority. That is nothing but an aging process if it results in a starvation. Okay, so this will take a quite little time, so that leads to an increased complexity. And one more thing, this aging technique is not effective when the number of waiting process is more than the available resources. If the number of resources is very small, if the number of resources is of amount, for example, 3, if the number of processes is 10, if it is requesting these resources, at that case, this aging technique is not effective. Okay. And one more thing, it is unfair to the newly arrived process because it can prioritize the long waiting process. Okay, as a result, the new process has to wait while the long waiting process gets the resources. So, continuously, a new process that enters into a system will never get a resource. So, these are the limitations of aging. So this is one more fixed priority scheduling. So we'll take a queue. Okay, in that queue we'll assign a fixed number of resources. For example, P1, P4, and then P5. In that particular queue, we'll assign a fixed priority. The priority level equivalent to 1. Okay, and then we can go for one more queue, that is queue number 2, and we can take some other process, that is P10 or P7 or P2, etc. Like this, we'll assign the priority number equivalent to 2. So while the execution starts, all the processes in the first queue should be completed before the second queue, because the first queue have a higher priority than the second queue. So this we call it as a fixed priority queue. Okay, this is one of the technique of an aging technique. And thank you. I hope so I have delivered whatever the things I have known. And if you have any doubts, you can ask and you can post your questions.
Okay, thank you for your presentation.
Listen, starvation is the thing is that the process will never get the resource for a quite indefinite period of time. Okay, a deadlock is a situation that if a process requests a resource at a particular period of time, that resource may not be available because it is assigned to some other process. Okay, so suppose in current scenario, if a cycle exists, if we draw a graph, if a cycle exists between the process P1 up to Pn, the process resource R1 up to Rn, if a cycle exists, we can say that there is no safe sequence. So we can automatically determine that a deadlock will definitely happen. Okay, so there is an explicit scenario that if the number of instances of resources may be of n numbers, instances of the resource may be n numbers, So even though if a cycle exists, there is a possibility for that the deadlock will never occur.
Hello, hello. I'm sorry, we have some problem in our office. The electricity is down. I came from other office, other STEKOM in the other branch. You may continue your presentation, but Novita is not here because his office is the electricity is shut down. Okay, you may continue, Miss.
Can I conclude the session, sir?
Yeah. Okay. Pardon me.
Shall we conclude our session?
Oh, okay. Please conclude. Wait a second. Wait a second. Uh, uh, Maybe you can read the on the chat. There is a question from the student. Maybe you can answer the question chat in the chat in the Zoom chat. Okay, maybe I will read the question. How can we effectively differentiate between deadlock and starvation in congruent system? And what are the key strategies for reviewing and analyzing this issue to ensure the optimal system performance and reliability?
So the deadlock occurs in the system where multiple resources are being used and the process need exclusive access to their resources. But in the case of the starvation, this can happen in the system with the resource allocation algorithm that prioritize the selected process over the leading and some process being the persistently overlooked. In this kind of situation, which is happened for particularly, the process may never be allotted the resource.
So starvation is nothing but when a process is denied necessary resources for an indefinite period, because that particular resource is actually held by some other process. So if the process never gets a resource for an indefinite period of time, we call this as an starvation. So to overcome the starvation, we are going for the aging techniques. If we automatically increase the priority of a process, automatically we can give the preference to that particular process. So we can provide that resource at a time. So normally the starvation process is nothing but a lower priority process, or the particular the process which is selected again and again as a victim will leads to an starvation state. If it's selected again and again as a victim, we will automatically either will pick up the resource that is held by that particular process or from some other process. Okay, so to overcome the thing, starvation, we can go for the aging technique.
Okay, thank you for the answer. And another question is, what methodology or tool do you recommend? What methodology or tool do you recommend for conducting through review and analysis of deadlock and starvation scenario in the system? And how we can apply this to mitigate these issues effectively? So I guess what is the tool?
In order to
Yeah.
yeah, you're
Mm.
asking the method, right?
Yeah.
So in order to avoid the deadlock, we are making use of Banker's algorithm,
Mm.
right? So in Banker's algorithm, we are saying that we are checking safe sequence. So if there exists a safe sequence, we can allocate
Mm.
that particular resource. If there is not a safe sequence, we doesn't eliminate the sorry, we just eliminate the if there doesn't exist a safe sequence. I'm sorry that if there doesn't exist a safe sequence, we cannot allocate the resources to that in a particular. So we can check the occurrence of a deadlock with the help of a Backus algorithm. That is, before a deadlock occurs, we are checking the safe sequence. If there exists a safe sequence, we can assign the resources in that particular. So if the safe sequence is, for example, P0, P2, P3, first the resources will be allocated to P0. And after completing that work done by P0, we just pull up all the resources held by the resource P0 and assign to the next process. Okay. So the safe sequence only says that whether we can assign the resources to the process or not.
Okay. Thank you for the answer, and I guess there's no another question. I guess maybe we came to the end of this visiting lecture. So we can close this event, and we are sorry for the problem in our. Hello, yeah. Hello.
Yeah, yes, please.
Aduh, I'm sorry, we have some problem in here. Because sorry, we have some electricity problem in our campus. Uh, so I guess we came to the end of this session, and we are very
Katanya udah end
thankful
loh.
for the
Katanya udah end.
speaker, and for the team, because we have also thanks for the international team in the India, because they also help us in taking over this Zoom. And okay, I guess we can close this session. Mm, okay, there is no tuh. Okay, I guess that's it. We can. I'm sorry for the attendance link is also cannot be provided, because our campus is done and I'm not in the campus. I'm in the other campus, the campus that do this visiting lecture. The electricity is done, so there is no attendance link, because the link is came from that office. Okay, I guess we can end this visiting lecture. I'm sorry for this problem. We are not apa.
Keluar aja ya. Lo tunggu lo.
Okay. Okay. I guess. Sorry. I guess we can leave this visiting lecture right now. Thank you and bye bye.
Thank you.
I'm sorry.
An opportunity.
Yeah.
Yeah, sir. Thank you. Thank you for giving me this opportunity to share a few knowledge with your students. Thank you for one and all. Thank you.
Okay. Thank you.